Okay, welcome back. Dr. P here. And in this lecture, we'll take a look at using electrophilic aromatic substitution in synthesis. So last time I gave you guys some hints for things to think about for planning electrophilic aromatic substitution syntheses. So let's just look at some example problems. Okay, so this is going to be propose a synthesis for each of the following molecules. You must start with benzene. But you can use any additional reagents necessary. All right, so let's take a look at these. So the first one is actually awfully similar to one of the examples I gave. Last time. We'll go with that. And let's see, I think I'm going to do 4 here. So this will be the first one. And then the second one. And then the third one here will be that. And then the fourth one, the thing is kind of tricky here. There we go. All right. So feel free to pause now and give these a try. Again, just some more practice, and of course we'll do more practice synthesis problems when we meet in person as well. All right, so okay, I'm going to assume that you've given these a look over, and now let's take a look at some of these problems here. So here's my target for number 1. Now, one thing that's good to do when you're looking at these electrophilic aromatic substitution problems, excuse me, is to figure out what do I have on the final product here, and what would be the directing properties of what I added. So I know bromine is an orthopara director, and I know ethane is also an orthopara director, but these are meta to each other. So I have to have started with something that will enable me to put a bromine meta to it. And so what we could do is the following. I'm not going to necessarily do retrosyntheses for all of these, but I will talk about my thought process. So I look at this and I see, okay, I could have had, heck, I will do a little retrosynthesis here. I can make this from this, and I can make this from that, and I can make that from benzene. So that is really what I'm doing here. So then I'll brominate, and this is one that I mentioned last time, for you have to pay attention to the order in which you do the reactions. So here you need to acetylate first, then brominate. So now the bromine will be meta to the acetyl, and then reduce. And there's our final product. Okay? All right. So let's go ahead and take a look then at the next one. One, two, three. Cl. NH2. Again, all of these are meta to each other, yet none of them is a meta director. So again, I have to think about how I'm going to do things. Now, what if, and again, maybe I will do a little retrosynthesis here. Because I have years of experience doing problems like this and writing them, I know that probably my reduction, so taking this guy and reducing it to my final product, will be the last thing I do. And now I can look at this and say, aha, I have something where I've got a meta director and another meta director, and I've got my chlorine there. So I'm going to add the chlorine last. Why am I doing that? Well, the chlorine is going to be the strongest group in terms of direction. So if I added my chlorine first, I'd be getting an ortho or para, but it needs to be meta. Let me just write here retro. All right, so then what did I have to add first? Well, the first thing I had to add was my propanoyl group here, because if I added my NO2, now that is strongly deactivated, and I can't do a Friedel-Crafts on that. Remember, that was one of the limitation on the Friedel-Crafts acylation. It has to be benzene, halobenzene, or an activated benzene. So what is this going to look like forwards? So we'll go ahead and start with benzene. And 1, 2, 3, Cl, double bond O, AlCl3. And then I'll do HNO3, H2SO4. NO2, and then I'll do Cl2, AlCl3, and then lastly I'll reduce, and so I can do zinc with mercury amalgam, HCl, AQ. And these are, again, just zinc and aqueous HCl is going to reduce my NO2, so they're close enough that I'm going to say that reduction will work. And there's our final product. So 1, 2, 3, 4 steps, but you had to do them in the right order. All right, now let's look at number 3. Let me just make sure you guys saw all of that. I'll put that back in frame. There we go. Okay, now let's look at number 3. All right. Well, this seems relatively straightforward. I could go ahead and do my bromination followed by an acetylation and then reduction. So I might be thinking of using Br2, FeBr3. That's going to give me a Br. And now I'll do my acetyl chloride and I'll get a mixture of products. Oh crap. What have you done, Wayne? What have you done? Okay, now depending on the problem, I might give you a problem where I say, if you get a mix of ortho and para, you can assume you can separate them. But what if you can't? What if you can't separate these? Well, then what we have to do is use a blocking group. So what we're going to do is we're going to stick something on the other end, and we're going to keep it from allowing us to put something para. So the way it's going to work is this. We're actually going to add the AlCl3 first. Sorry, the acetyl chloride and AlCl3 first. Incidentally, if we had switched the order here, we would get a meta-bromine, but if we switched the order, if we added this first and then reduced, we would be getting, again, a mix of products. So why don't we acetylate first and then reduce, because that will give me now my ethylbenzene. And now my ethylbenzene I'm going to sulfonate. And this is my blocking group. It's big, so it's going to go para instead of ortho next to the ethyl. Now, nothing can add para here, so I can go ahead and do my Br2 and FeBr3. And then in the last step, I'm going to use dilute H2SO4, dilute acid, and that's going to remove the blocking group. So we're making use of the fact that the sulfonation reaction is reversible. So this is kind of a cool thing, and you don't always have to do it, but it can be useful. You'll actually see that when you do the Friedel-Crafts reaction, you tend to get para anyway, even with small substituents and relatively small electrophiles. The acyl ion there is actually, or acylium ion is actually pretty small, but compared to like a T-butyl cation. But anyway, yeah, so that's how a blocking group works. So you may remember last semester I talked about good synthetic organic chemists, good synthetic organic chemists use protection in their synthesis. And I talked about the use of protecting groups. Well, this is similar, but this is what we call a blocking group. So it's like we're sort of blocking one position, we're kind of protecting it, but we're not protecting a functional group, we're just blocking off part of the molecule. All right, last one here, and this one is tricky. I've got 3 bromines and they're all meta to each other. How am I going to do that? Well, the key here is to think back to those aryl diazonium compounds. What if I took benzene and I'll nitrate it, actually I'm going to cross that off, I'm going to put it right up here, doesn't matter where it goes, but so there's my NO2, and now I'm going to reduce now I've got a really strongly activating group and it's an orthopara director. So I can go ahead now and brominate 3Br2 FeBr3 and now I can use my NaNO2 sodium nitrite and hydrochloric acid. That's my nitrous acid, and that will give me now N2 with the positive charge there, and then H3PO2 hypophosphorus acid removes my N2 and replaces it with a hydrogen, and I have my final product. So if you see something like this where it looks like, gosh, all of these are orthopara directors, and it's not like, you know, my first problem here where, yeah, they're both orthopara directors, but this guy could have come from a meta director. Here they're orthopara directors, but gosh, what am I going to do? Put something that's an even stronger orthopara director on the ring first. And that is we nitrate, we reduce to make the amino group. So now this aniline aminobenzene is strongly activated, strongly orthopara. Put bromines in both ortho and the para position. And then we make the aryl diazonium ion, and then we take it off. All right. So practice these, and we'll go over some more when we meet in person. All right, so keep working on that synthesis, and until next time, stay safe out there. Bye now.